You join me on the north bank of the River Clyde, some 6 miles down the water from Glasgow, in a town appropriately called Clydebank. I'm standing on the site of the former John Brown shipyard, overlooking a patch of water called the Basin. When the ship hulls were launched, they were manoeuvred into the basin for fitting out. Towering above me is the enormous Clydebank Titan crane, which was used to lift heavy objects such as engines and boilers on board the ship so they could be completed. In tonight's video, I hope to show you my efforts to recreate the crane using vintage Meccano and animating it using 3-stepper motors controlled by an Arduino. You will also see me use artificial intelligence to try and help me write the software. So let's get on with the show. Craig Lennox reporting for WOZAG News for Merg TV. Clydebank has a rich industrial history of building ships and manufacturing sewing machines. The Singer factory was completed in 1885, employing over 4,000 workers at its peak, and was capable of manufacturing 10,000 machines a week, and over 36 million machines by the time it closed in 1943. It was renowned for many things, including a clock tower, with the largest clock face in the UK at the time, and its railway station is the last remaining one in the UK named after the factory it served. For those collectors of railway-related trivia, the others were Eurolite Halt in Kent, serving the factory which made asbestos pipes, chimneys and windows boxes, which closed in 1961, Acro Halt in Essex, which served the factory of the same name, which itself was named after the founder Arthur Crowe. It made a variety of industrial products, but most famously will be the ubiquitous Acro Prop. That station shut in 1964. Daimler Halt in Warwickshire closed in 1965. Wedgwood in Staffordshire closed in 2004. IBM Station in Renfrewshire closed in 2018. And Redcar British Steel Station in North Yorkshire closed in 2019. Shipbuilding was focused at the J.G. Thomson Yard from 1871, bought over in 1899 by John Brown and Company Limited, and further west in Clydebank at the William Beardmore Yard. John Brown purchased his yard as an outlet for his successful armour plate rolling mill in Sheffield, as the yard already had orders of £3.1 million for naval contracts and £1.4 million for merchant ships. Many famous vessels were launched from here, including Cunard's Carmania in 1905, Lusitania 1906, Queen Mary 1934, Queen Elizabeth 1938, and the QE2 in 1967. Naval vessels included HMS Leviathan, a Drake-class cruiser in 1901, HMS Hood in 1918, HMY Britannia in 1953, now a tourist attraction in Leith, and at its peak it employed 10,000 workers. The shipyard and singers used to coordinate different clocking off times to avoid overwhelming the town. I have been fortunate enough to work in Clydebank for 30 years so far, and was pleased to move 3 years ago from an office with a view of a rough cast wall to arguably one of the best views in Scotland. This led to a mild obsession to learn more about the Cran and one day make a model of it. The Clydebank Titan was designed by engineer Adam Hunter, 1869 to 1933, of Sir William Arrow and Company. Hunter was apprenticed aged 18 under James Tuitt of Tancred Arrow, and for his first 3 years worked on the construction of the Forth Rail Bridge. At 19 he designed his first crane, which was a hydraulic swivel type for use on the work yard there. He was transferred to the London office in 1890 to begin work on Tower Bridge as an engineering assistant, still under Tuitt, who was by then Arrow's chief engineer. By 1895 he was promoted to chief assistant, and on Tuitt's death in 1906 he became chief engineer. Through his career he was responsible for a vast number of key projects including London Southwark, Blackfriars, Waterloo and Albert Dock bridges. Internationally he built a power station in Athens, lock gates on the Nile, railway works in Nigeria and bridges in Basutoland and Denmark, to name but a very few. Hunter began work on the Clydebank Titan in 1905 with drawings for the 4 cylindrical piles which are driven down 75 feet. The tower is built on 4 legs forming a 40-foot square which tapers to 35 feet at the top. It is 120 feet tall. The boom is 240 feet in length and in total weighs 880 tons. The live ring sits on 75 forged steel conical rollers, and the centre pin for the mechanism is 14 inches in diameter and 13 feet long. 6 tons of nickel slag ballast is stored on the short arm. The speed of the main lift, under 150 tons of load, is 5 feet per minute, and a full rotation takes 5.5 minutes. The build was concluded in 1907, costing £24,600, which would be about £4 million today. On completion, it was the largest crane of its type and was the world's first electronically powered cantilever crane. It was originally designed to lift 150 tons, but was eventually capable of lifting 223 tons after an upgrade in 1938 to lift the heavy long-range gun turrets for ships such as battleship HMS Duke of York. The Titan was refurbished as a tourist attraction in 2007 at a cost of £3.75 million, with a coloured light display, a visitor centre called the Drawing Office, and a passenger lift with emergency stairs and a bungee jump. Sadly, it is temporarily closed to visitors due to funding problems. I decided that the most appropriate medium for constructing my tribute to the Titan was vintage Meccano. What else? My model is constructed using most of the contents of a Meccano Set 9 that was carefully brought to life by generous members of the Meccano Society of Scotland. Additional parts were from kind donations from members or bought from traders. The model has a length of 40.5 inches along the boom and is 33.5 inches from base to top of the motor room. This gives an approximate scale of 1:73, or just a shave off 00 scale at 1:76, conveniently allowing for a range of accessories to be used with the crane. Being my first proper Meccano model, the engineering is basic, but I hope conveys the look and feel of the prototype. The tower is a simple construction of girders and strips, topped with a platform edge with 12 trunnions on which is mounted a 4-inch geared ball race. Rotation is achieved using chain, driven by a stepper motor with a simple tensioning device made from rods and brass couplings. The boom uses girders as rails for carrying the crab on its 3/4 inch flanged wheels. The Clydebank Titan machine room appears to have a lower profile than other local Titan cranes, perhaps because it was electrically powered rather than steam. This I tried to replicate using 8 of the 5x3-hole flanged plates in blue to reflect the current colour, and included the 3 windows either side. Inside was a bit of a squeeze, but includes the 2 pulleys at the front used for load lifting and the crab positioning, and in the back are the electronics. As a member of MERG, the Model Electronic Railway Group, I was keen to merge the 2 interests. The Arduino Nano is mounted on a 5x7-hole flange plate, and the 3 stepper motor controller boards are mounted on 3 flexible 5x5-hole plates. This allowed for flexing into the confined space and easier removal for maintenance. I chose to power the crane using 3 of the small and inexpensive 28 BYJ stepper motors, which are supplied with their own motor controllers that plug into the Nano. The motors with controllers work out at about a tenner for the 3 of them from all your usual sources, and Nanos are just over a £5 at the time of filming. I also indulged in these Nano adapter boards at about £3 each, which I found simplified matters for me in the development stage, and also were handy final mount, avoiding short circuits against the metal of the Meccano. Operation by remote control requires 6 wires for direction, 2 for each motor and 2 for power, so I opted to use standard Cat5 network cable for the conductor. This approach allows for the use of coiled Cat5 on the crane to permit rotation and ease of uncoupling for transport using female-to-female connectors. So this is the control box for the crane. On the left, as you can see, we've got 8 buttons for sounds, and on the right we've got 4 buttons for up, down and left, right, and also we've got rotation on with the blue buttons there. Inside we've got connector for the Cat 5, power coming in, the sound module and the speaker, and that's about it. The sound module was bought for just over a tenner on Amazon and uses an SD card to store the samples. The samples, as usual, were collected from the BBC Sound Effects website. These included recordings from the Clyde Crane engine room, the QE2 horn, some shipyard ambience, and a ship launch. The 4 others are for a steam train and a lorry. For the software, I wanted to be able to control the stepper motors from the Arduino so that I could operate them in both directions at roughly scale-looking speeds and simultaneously. I had heard that AI and specifically ChatGPT could be used to write software, so I thought I'd check that out too. I had looked into controlling stepper motors and found that the standard stepper control program in the Arduino library did not meet my needs, but a quick search around found that Excel Stepper did. It supported acceleration and deceleration, multiple simultaneous steppers, a variety of motors, and very slow speeds could be supported, so I added it to my library. The software requirements therefore were to control 3 28BYJ stepper motors with the ULN 2003 control boards, using the Excel Stepper library, 6 momentary push buttons, clockwise or anti-clockwise movement, at roughly scale looking speed, and simultaneously. It is important, much like with using search engines, that you are careful what you ask for. So I made a first attempt at a question for ChatGPT and clicked go. This is the actual speed, view of it churning out the code with notes on the code also. At the bottom of the screen I am typing a follow-on question asking for a wiring diagram. As you can see, it's quite happy to list the components needed, exact locations of where you should be wiring up the motors from the Arduino to the control board, and also the push buttons where they should go. And then it gives you this visual representation of how that should look, which you can actually copy into your code. These next clips are showing some of my earlier conversations with the AI, all of which is saved automatically, and demonstrating that mistakes can be made. Interestingly, these mistakes are not being made now when I ask the same questions, maybe showing some machine learning. I should have asked in my original question for the code to use the Arduino's internal pull-up resistors, but this was soon sorted. I then noticed that the code did not have the correct configuration for my stepper control boards, which needed 4, not 2 inputs each. When I initially asked it for a pin diagram, you can see it earmarked Arduino pins 8, 9, 10 and 11 for each of the 3 motors. It was quite apologetic and fixed it. I had already wired the board up, so being lazy I asked it to move the pins around in the code to fit my wiring. ChatGPT then made a mistake, thinking that my Uno test board had 1 more pin than it actually had in reality. I then looked to see if ChatGPT could support some additional questions about the code, like how would I be able to change the speed of the motors. It was quite happy to tell me to change the parameters in set speed. When I uploaded the code, it was clear that acceleration and deceleration didn't work. I now see that I should have specified that in my initial question. It solved that by using the move command in the library rather than the set speed and run speed commands. It even came with a nice explanation. Here I have asked it to repeat the final code, including a header with some notes on the code and a wiring diagram to aid my memory when revisiting it. Once ChatGPT has finished, just copy the code with the click at the top of the code window, open up your Arduino IDE app, paste the code in and give it a quick check to see if it's all there. Then check that we will connect with the correct type of microcontroller, in this case a Nano. Then make sure I have downloaded the Excel Stepper library by opening the Library Manager area. Type in the search box Excel stepper, mine is already installed. You would just click the install button and load it up. And then a final check to see if it's installed in the IDE's include area. Note the pre-installed basic stepper, and then further down in the contributed libraries, the Excel stepper. And then a quick test to see if it compiles without any errors, which it has done. And then upload it to my Arduino. As another test of ChatGPT's usefulness, I asked it to tell me more about the Excel stepper library, and it came up with these highly useful notes on how it can be used and even some example code. I thought that was a great teaching aid. In this there was some gentle reminders to include the Excel stepper, how to set the maximum speed and acceleration, commands to move the stepper, and the commands to run the stepper. A little bit of advice on how to run it at a constant speed and how to run to a particular position. And then, as I have used, how to run multiple steppers. And finally, a bit of example code to run just one motor. And now a quick run through the completed code. This is the header with explanations and pin wiring diagram that I'd asked ChatGPT to include. As I said, just so you don't forget when opening it later or handy if sharing it on. Here it's reminding which pin for which buttons on board, connections, and ground and power. And a wee reminder that it's also using the internal pull-ups. Make sure you include the Excel stepper. Then on to defining the pins on the Arduino that send to each of the 4 inputs on the stepper motor controller board. Next it defines the Arduino pins A0 to A5 for the push buttons. And as it says, the 3 instances of the Excel stepper for each of the 3 motors. This area sets up each stepper motor's acceleration and deceleration and maximum speed. In this case 500 and 1000, which is easily changed, a bit of trial and error, and only up to a point. This sets the internal pull-ups, and then we're on to the loop itself, which for each of the 3 motors, a short if, else, if loop, checking if button 1 clockwise is pressed, then move 1000 steps clockwise, else, if the counterclockwise button was pressed, then move 1000 steps in the opposite direction. This is repeated again for the other 2 motors. And then finally, the run commands for each of the motors to enact those moves and then back round again. That was the final code for the crane as it stands, but I thought I would chance my arm to look at the potential for automatic movement when the crane was not being manually controlled. For this to work, the Arduino needs to have a setup routine on power-up that determines the maximum and minimum ranges for each of the motors and a starting point. This is often done with microswitches, but I asked ChatGPT to add some code to do this manually and save the results in the EEPROM. It was happy to do so, and it did work, but I ran out of time before an exhibition to add the automatic movement after any delay code. Here is a quick demo of the crane in action, including some of the sound effects. This is the finished model at the infamous Meccano Society of Scotland annual exhibition at Summerley Industrial Museum in Coatbridge. I thoroughly recommend a visit to this museum, and the next Meccano show is on the 14th and 15th of September.
My conclusions then on ChatGPT as an assistant to coding. Well, it was very fast, as you saw, not error-free, but quite content to fix the errors when pointed out. I think it helped to have some knowledge of coding for the Arduino to spot these mistakes. Building with the vintage Meccano was great fun, and as we all find when making models, adding extra value with sound effects and movement is well worthwhile. That's all from me, except to remind viewers that there are over 160 very helpful videos that you can find either via the link from the WOSAG website at wosag.org or from within YouTube searching for the WOSAG channel WOSAG. For example, there's a really helpful video called An Introduction to Arduino Libraries by Davey and a two-parter on the Arduino serial monitor. And I counted 6 videos looking at different ways to add sound to your project. So take a look. Now all I have to say is a big thank you to those who have helped with the crane and this video, and take it away, Fiona.